Let me see which slide. Let's see. Which slide I want to start with. We already dealt with Doppler effect, so that's that one.
Can I ask you a few questions about the homework?
Sure, absolutely. Let me find which slide I need to be on. Okay, there it is. So let's go back to this one, and we'll start from current slide. Okay. Now, before we get going, before I answer your question, let me make these comments, my more sad songs here. The spring schedule is an awful mess. And people are already registering for spring, but there's still a lot of corrections that need to be made. I've got all the Math 098 corrections made, I think, knock on wood, and most of the 100, which are the worst. But I've still got a few more to go there, and then I've got the other upper level classes, and hopefully I can get those done without too much problem, because those are in bad shape. This is Ashley, right? Mm-hmm. Okay. Now, the upshoot of all that is I'm this far behind in grading, because just about every minute I'm in the office, I'm working on the schedules. And I can only work on grading when I'm not in the office, and those are few and far between times. Tyler is here. Okay. Now. Oh. And let's see. What's that?
I gotta go do something with the team.
Okay. This is Shannon. Okay.
I need to take this.
What's that?
Take this.
I can't hear.
Or do I need to?
That's the test I'm going to hand out tonight.
All right.
Yeah. Do you want it now? Okay. 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 All right. So the upshoot of all this is I'm way behind on grading. So even though you've turned things in, some of it may be graded, but I don't have it on Blackboard yet. Others of it I don't have finished grading yet. And I'm hoping tomorrow I have 4 hours of office hours, or that minus lunch and a few things. I'm hoping, and I've got to set up a lab for tomorrow too, but it won't be too bad. But I'm hoping that I can get most of those corrections made tomorrow, which means if I don't have them finished by Friday, hopefully I can get them made, and then I'll get back to grading. And I'm going to grade like crazy. I'm going to grade tonight as much as I can. I've got 2 stops to make on the way home, but after that, I hope to be able to get some grading done. So I'm awfully sorry about this. Usually it's not this bad, but y'all maybe Tyler knows, I don't know, you may not because you're in upper level classes. This term, fall term, they changed all of the developmental, all of it, and put labs with it and stuff. So we had a mess doing this schedule. And then that didn't work too well, so they went to do it a different way for spring. So now it's another mess, and that's where this other person is trying to put things in, and she's just not doing it right, and I'm having to correct hers and then add the others, so it's really been bad. But I'm hoping I'm more than halfway there getting it done. And today, when I had hoped to get some stuff done, my computer, they were working with it the whole time. The student came by for advising. I mean, it was just, I got 0 scheduled stuff done today. Hopefully I can get it done tomorrow, okay? Or at least most of it. All right, now to your questions. Did you have one? Which?
Number 15 on page 442.
442. Now let me get something in place here so I can hold it. 442. Oh, that's the page I'm on. Okay, 15?
Right.
Okay, 2 construction workers stand 112 meters apart. Let me get my pen set up. Okay, so here's a construction worker. There's a hard hat on. Oh, that's not much of a hard hat. There's a hard hat. And here's another one over here. Okay, with a hard hat on. Okay, and this is 112 meters apart. Okay. One strikes a steel beam with a hammer. So here's a steel beam. I don't know where is it going. So he hits it with a hammer. Okay. How long does it take for the other to hear the sound? Assume the velocity of sound in air is 345 meters per second. So the question is, how long? Now, what is that referencing?
Time.
Time. So this is the thing we're looking for. This is the unknown here. And we're given the speed, velocity of sound in air. So V sub S is, and this is speed of sound, 345 meters per second. Okay. And they're 112 meters apart.
Wait, so I thought V sub S was like the velocity of the source. What did you say that was?
Okay, that's why I said here I'm using it as velocity of sound. Okay, you don't have to call it VS if you don't want to. I realized as soon as I wrote it, in Doppler effect, they use that as source. So, yeah, that's just velocity of sound. Okay? This let's call our distance. Is that okay? Okay, just to have something to call it. Now, let your units be your friends here. The time is going to be measured in seconds. So we have velocity that's in meters per second is equal to distance in meters divided by time in seconds, right? Let your units help you out here. We're looking for time, so how do we solve for time?
We say time equals the distance divided by
Distance divided by velocity, exactly. So our distance here is 112 meters divided by velocity, 345 meters per second. And the meters are going to cancel out, and 1 over 1 over second is seconds when you invert and multiply. So if you got a calculator, 112 divided by 345, it's something around 0.3 maybe.
yes,
What you got?
0.325 seconds.
325 seconds. All right. Is that what they got in the back?
Yes.
Okay, got it.
Okay. Well then, maybe that's, I also wondered about number 19, but I think I was just missing the obvious. Okay, so number 19 is the same type of problem, correct? You don't have to work it.
A construction worker 30 meters above the ground drops his hammer. How long does his shouted warning take to reach the ground if the speed of sound under the condition? Yeah, exactly.
Okay.
Yeah. Only how it went down. Yeah, okay.
All right, may I ask you one more?
Say again?
May I ask you one more?
Okay, sure.
Number 13.
On the same page?
Yes.
Okay.
My answer was just really close to the books, but not quite. So
All
I
right.
was just trying to make sure I'd set this up correctly.
I forgot to put the page number before. That was page 442. I forgot to put everything on it. Page 442. And this is 16.4 problems. Problem 16.4. Okay.
Number 13.
13. A jet airplane taxiing on the runway at 13 kilometers per hour. So I don't draw very pretty planes, so let's just have it something like this, Okay, taxiing on the runway at 13 kilometers per hour. That's the velocity, right? V is equal to 13.0 kilometers per hour. Okay, it's moving away from you. So here you are back here. Okay, moving away from you. The engine produces a frequency of 660 hertz. So the frequency produced by the plane is 660 hertz. Those are per seconds, by the way. In negative 6.0 degree Celsius air, not anywhere around here. This is temperature. Capital T is temperature, okay, air temperature. What frequency do you hear? Okay. Now, there's several things that we have to deal with here. This is a multi-mixed problem, okay? The first thing we've got to do is from back on page 436. We have to adjust the speed of sound in air using the formula on that page. Right? Because they didn't tell us the speed of sound. Okay?
So maybe that's where I missed it, because what I did, I forgot to use that formula. I just went and looked that air is normally 331 meters per
Right.
second at 0 degrees Celsius, and so I just then said that times
Okay.
the negative.
You're going to be off just a little bit then.
That's why I was off then, because
Yeah.
I said that times -6 and came up with an answer. Okay, that makes sense.
Okay.
That's
So
what it is.
it's just a little off, right? That's it. Yeah, you have to do that. You have to subtract 0.61 times 6, which is about 3.6 from 331. So that would be about 229 or something, 228, something like that, maybe 227. That's going to be your speed of sound, and then from there on, it should work. Is that enough?
It is, yes.
Okay. All right. Good deal. Any others? All right. Now, have I managed to lose my place? I think so. But I got it back. Okay. I'm going to erase my ugly drawing here. Is that okay? Y'all say, yes, please. Okay, never mind. Okay. All right. If no more questions, then let's go to resonance. 16.5. All right. Now, has anyone ever heard of resonance before? Did we talk about it a little bit? I can't recall. Okay, not at all. Okay. Has any of you ever heard of a thing called a tuning fork? Okay. That's something you wrap on the side of a table or somewhere, and you hear it go, and it holds a note for a fairly long period of time. Okay? That's the natural frequency of an object, such as a tuning fork, is the frequency at which it vibrates when struck by another object. And tuning forks are usually very precisely made so they hit one fairly pure note. Okay. Now, when you're playing an instrument, they mention a guitar, same is true for piano, a lot of things. But let's take a stringed instrument like that. Believe it or not, a piano is a stringed instrument because underneath that thing are these metal chords that are held at tension, and that's what the hammer hits, and that's what makes the notes happen, okay, the sound produced. And we're not going to get into this, but the frequency that they hit depends on the length of the cord, the diameter of the cord, and the tension in the cord. And what you do, the length and diameter are pretty much fixed, and you adjust the tension to get right on frequency. And if you've ever watched a piano tuner, they are very talented, skilled people. I couldn't do it. My discrimination among frequencies is really, really poor. Theirs are usually quite good, okay? And they can hit the note and adjust the thing, and they will actually see or hear the piano chord or the guitar chord vibrate with the tuning fork when they're right on frequency. That's called resonance, okay? This vibrating chord, if it's right at the same tension and everything else, it will get this other one that's vibrating at the same time. That means you're right on, okay? So what it's doing is you're forcing a vibration by setting up your plucking the cord or hitting it with that, whatever you're doing, okay? Now, consider two objects such as tuning forks with the same natural frequency. They're set close together. If you start one vibrating, the other one will start vibrating if they're close enough together, and that's because this frequency will get that one going without striking this one. You know, it actually happens. Same thing true with the chords and things like that. What you're setting up is that's called sympathetic vibration or resonance. So resonance, another name for it, is sympathetic. I can't write. Vibration. Okay. Now, it's not, oh, I feel sorry for you, sympathy. It's doing the same thing, which is really what sympathy means. Pathos is feeling or something like that. Sympathy means feeling your pain, you know, feeling the same way. Sim is the same. So your sympathetic vibration, the vibrations are the same. That's why they set it up that way. Okay. And that's how you go about tuning everything. Now, my knee has really been stiff lately. I don't know why. It's fine when I'm walking and stuff. When I've been sitting a while, stand up, it hurts like crazy. As soon as I move around some, it's fine. It's the craziest thing. I don't know. All right. So, how was I getting up anyway? Now I've forgotten. There was a thing, but all right. It doesn't have to be sound always, but that's what we're used to. And when you're doing sonography, I'm pretty sure someone comes in and calibrates your equipment. I don't know if you'll wind up doing part of that yourself, but I bet you what you're going to do is making sure the frequencies are matching up. Now, it's probably done electronically. You don't have to worry about it. But there's all sorts of ways that resonance happens. And I thought maybe I had suggested some of these before. Have you ever pushed the child in the swing? Okay? Have you ever pushed when the swing was coming up to you and there you go to push? That doesn't work well at all. You're not in sync with that. Okay? What you do is wait till it reaches the very top, and then you just give a little push, and now you're increasing. Now, some of you guys, and maybe gals too, perhaps have pushed off a car that was stalled before. Can you push a car? Not just with brute force, but what you do, you get it rocking. Right? And right when it rocks forward, you give it another little push. Rocks back, and right when it rocks forward, you give another push. What you're doing is getting on a sympathetic frequency with the car's natural frequency. And if you push right at the right time, just like pushing the kid in the swing, then it moves and moves more easily. And you're not having to push the entire car, you're letting its sympathetic resonance do that. All right. There was at one time, and I think they may have a picture of this in the book. I thought they did, but now I can't. Yes. If you turn back to page 450, this is the Tacoma Narrows Bridge across Puget Sound in Washington State. There was a bridge put across there. Now, if you've ever been out west, San Francisco is especially like this. I've not been in Seattle that much. Only one time I recall, so I don't remember. But I know in the Pacific, because the wind coming over the Pacific Ocean, big ocean, nothing in its way, and the wind comes in pretty strong and pretty constantly, same direction, pretty much similar speeds just about all the time, okay? San Francisco, they call Chicago the Windy City. I'm not convinced San Francisco is a windier city. But even Chicago is right on the lake. And that wind comes across there. That's why that is such and then the prairie is on the west of it. So, and we have prevailing westerly winds, so they come across that way. Oklahoma, wind goes whipping around the plain, all that kind of stuff. Wind's coming. So they built this bridge over the Tacoma Narrows, the place where the land was close together, put the bridge over so you could cross over without going all the way around Puget Sound. The engineers, either no one had ever heard of it or no one thought much of it, but they built the bridge and they just happened to build it in such a way so that the bridge's natural frequency, everything has a natural frequency, the natural frequency of the bridge matched the natural frequency of the wind coming in at certain times, And what happened, people riding on the bridge noticed that the bridge just rocked a lot, okay? They didn't know why. They nicknamed it Galloping Gertie, okay? Well, they got Gertie, it just run, assonance with galloping, okay? And after a while, the winds, one day or one period of time, the wind was very constant at that frequency for several things. The bridge started rocking and rocking, and literally the picture you see here is the bridge tearing itself apart. Okay? You would not think that possible, but it happened. The bridge literally destroyed itself just because it had the natural frequency, the resonant frequency of the wind. After that, bridge engineers started paying attention to what natural frequencies of the wind were and calculating that in their design so that they didn't do everything that was very close to that same natural frequency. They'd have to put a few things in there to make sure they were on a different frequency. So that literally happens not just in sound, but in other things as well. Now, we don't usually watch much television at all, and certainly not that many movies on TV, but for some reason, I was doing something and had time to kill and watched Miss Congeniality, I think it was. Y'all seen that movie? No. It's a dumb movie, but it's funny. Sandra Bullock was an FBI agent who was playing a part of not very feminine at all, but a good looker. And they had word that some sort of terrorist event was going to happen at a Miss USA pageant, supposedly Miss America pageant, but they couldn't say that. So were going to put her undercover as a contestant in the contest, and she had a lot of work to do, okay? But she had to have a talent, and something that she was really good at. Yes, the glasses, right. and she was playing a song on the glasses, and that's the picture at the bottom of page 443. What you do is set up resonant frequency, and you can do this with any wine glass, any crystal glass. Wet your finger and turn do your finger across the lip of it, and you'll get it to singing in its natural frequency. Okay? Put different amounts of water in it, and you can get the notes to be exactly what you want. And she played the glasses. That was her talent. Okay? So that even a dumb movie can have physics in it, right? And here's Jennifer Addison. All right. And that's that activity. And you can do that too and play with that. All right. That, I think, is all we need to do with resonance. It is. Oh, and by the way, I take it that y'all are only going to be sonograms, right? That's the only type of thing you do. But there are other technicians out there that deal with MRI, ESR, and you know what those things stand for? MRI? Imaging resonance. ESR, electron spin resonance. There are all these other devices that are based on resonance. And when they hit something on the right frequency, then they resonate, and that's what they are doing. Now, ultrasound is just doing sound. It's not necessarily resonant sound, but it is. But, you know, these other things deal with frequency resonance, okay? And in fact, any of you listen to the radio? What you're doing when you're turning that knob, you're aligning capacitors, so you're changing the resonant frequency. Because right now, in this room are probably hundreds of radio signals. Are you hearing any of them? No, I'm not. Maybe y'all are, but I'm not. But if you had the electronic set up, you could turn the knob a little bit. You'd hear this one. Turn a little bit more. You hear that. They're all in the room, but you set up your receiver, adjust it's a capacitor to adjust it, and you can get on the resonant frequency, and that's how you pick up those channels. You're just aligning the device with the resonant frequency of the signal, and that's why you hear it. Otherwise, the signals are like this, and they cancel each other out. But on the resonant frequency, they come in, and that's why tuning it a little bit can make it sharper, clearer, or whatever. Okay. We probably beat that to death. All right, let's move on to simple harmonic motion. This is 16.6. I guess I'll leave resonance up there for now. We aren't really using it. What in the world do we mean by this? Simple harmonic motion, I'm just going to call it SHM, simple harmonic motion, is a type of linear motion, okay, that in which the acceleration of an object, so the acceleration of an object is directly proportional to, have we used that symbol before? Proportional to? No. Is directly, that's what this stands for, is directly proportional to the displacement from the equilibrium position. Okay. Now, because acceleration is, the mass is fixed, and mass times acceleration is the force. So the force is directly proportional to displacement. I'm going to make it x now because there's a reason coming up later, not distance. And you can do this with F is equal to kx. You change the proportionality to equal some constant, and that's called the constant proportionality. Okay? You don't need to know all this, but that's where that equation comes from. If the force is proportional to or exactly equal to some constant times the displacement, you have simple harmonic motion. Okay? The classic illustration is that of a spring, and you have some mass hanging on the spring. Okay? And you take this and you pull it downward. That mass, you pull it downward. Now you've removed it from its equilibrium position. That's its equilibrium position right here. If you just let it hang there and settle out, that's where it's going to hang. If you stretch it this way, when you start pulling on that, you'll feel the spring is pulling back up, right? So the force is proportional to, so in this case, it happens to be a minus kx, because the force is pulling back in the opposite direction. You pull it down here, the spring is trying to pull it back up. If you compress the mass, till it's right here, that's getting uglier and uglier. Same mass, compress it here, what's the spring doing? Pushing back down. So it's always proportional. The further you pull, the stronger it pulls back. If you pull just a little bit down, it just pulls a little bit back. Compress just a little up, it just pushes down a little bit. Compress it more, it pushes back harder, right? Force is proportional to the distance from the equilibrium position.
Does this have to do with sound?
Okay, now it sort of does. Okay. You play a guitar? No. Okay. You've seen a guitar play. Okay. When you pluck a string, if you do it gently, then the string vibrates just a little bit, and you hear a little sound. Pluck it harder, it's a bigger sound. Same type of a deal here. The more the displacement from equilibrium, the greater the vibration. So it has to do with the same thing. That's not usually called simple harmonic motion, but it has got that similarity. Okay. Now, no, we're getting away from sound now. This is back to, this chapter is wave motion and sound. We're back to wave motions now, less on sound. Okay. Though sound does come into play a little bit on it. Okay. So, in general, the displacement of the object, okay, this displacement is this would be the displacement. How far it's removed from its equilibrium position. This would be the D up here too. So that's your displacement. The displacement of an object in simple harmonic motion is the distance from the equilibrium or rest position. That's where it would sit if you had absolutely no forces on it, net forces on it. Okay? Now the amplitude of the vibration, did we talk about amplitude before? Of waves? Amplitude is the distance from equilibrium. You remember when we talked about water waves? How high it is from equilibrium to crest. That would be the amplitude. Same type thing here. The amplitude of the vibration is the maximum displacement. Okay? So the max displacement would be equivalent to amplitude. Okay. We're going to get a little bit of that a little bit later. Okay? Now the period, remember period was capital T. Period. This goes back to our wave stuff that we were doing before. That is how many seconds per cycle. Okay, remember, reciprocal of that is cycles per second, and that's hertz. Okay, that you were asking about before. Okay, so frequency is 1 over period. Okay, it's the number of complete vibrations or cycles, which is not really a unit, per second. So usually we just say seconds to the minus 1, cycles per second, which is just a reciprocal of the period. Just hitting these keywords that we talked about before. Now, all right, here is a Ferris wheel. Okay, I've seen these at fairs and things, right? As the Ferris wheel turns, okay, this is sort of a dumb example, but it's certainly true. The simple harmonic motion of the shadow of a person is shown as on the PQ. Here's the line PQ. And here you are in your seat here. Okay? Now, when you were over here, your shadow would be right out here at Q, if the sun's coming directly overhead, right? And as you move up here, your shadow is moving this way, this way, this way, this way, but then starts coming back this way, this way, this way, this way, back here. So if you looked at your shadow, it would be doing this now, right? Just back and forth and back and forth. As long as the wheel's going in a uniform motion, constant speed, you go back and forth like that. Your shadow would be in simple harmonic motion. Okay? The frequency at which the deviation from equilibrium, so right here, that would be your amplitude. The time period that it would take to go from here to there, back to here again, that would be your period. 1 over that would be your frequency. So this has nothing to do with springs, nothing to do with sound, but it's the same thing, simple harmonic motion. Anything that repeats itself for whatever reason, because of the spring constant, because of the shadow of a moving circle, whatever it is, that's simple harmonic motion. And if you think about it, okay, temperatures are just about always follow simple, regular pattern. Coolest at night, warmest in the day, and it goes back and forth and back and forth. Seasons of the year, amount of sunlight, all this simple harmonic motion. Okay? Everything follows, a lot of things in nature follow simple harmonic motion. Okay? Now, another thing, and let's see if they have a picture of this. No, they don't. Let's go, let me sort of draw it here since I've already got it on the side here. A pendulum. Okay. Some mass down here, and you get it swinging. And it swings back and forth, back and forth, back and forth, following an arc like that. Right? That follows simple harmonic motion. Okay? Because it follows the same pattern over and over and over again. Have you ever been to McWayne Center? I think I ask this periodically. You know, do they have that big Foucault pendulum back in one corner there, hanging from the ceiling, goes back and forth. And if you looked at it day after day, or time after time during one day, you would see it actually rotates around. But that's a pendulum going back and forth. Grandfather clock, grandmother clock, the pendulum going back and forth, back and forth. That is, because it follows regular pattern like that, simple harmonic motion. Okay? Now, a few things about that pendulum. Number one, the period of the pendulum, T, is independent. Now, I'm talking about the pendulum here. Is independent of, believe it or not, the mass that's on the end here, this M. Doesn't matter whether it's a heavy thing or a lighter thing. Now, it has to be heavy enough to swing, but, as long as that, doesn't matter. You can put twice the mass there, still going to work fine. Okay? Now, its period is also independent of the amplitude when the arc is small. So the period is also independent of the amplitude, as long as the arc is small. If you get up more than a few degrees, then you're going to have problems, and that comes to play. But as long as it's a fairly short angle there, doesn't matter what the amplitude. So it's independent of the amplitude as well. And the third thing about it, here's the formula for it. The period is equal to, some strange numbers here, 2 pi now times the square root of the length of the pendulum over the acceleration due to gravity. Remember that? 9.8 meters per second squared, or 32 feet per second squared. Okay? Now that length, here's the length of the pendulum, that's all the period depends on. Now, my parents-in-law, one of the first years we were married, I think it was a Christmas gift or something, gave us what they call a grandmother's clock, shorter than a grandfather's clock. And it always ran slow. So I tried like everything to go out to its max, trying to improve the thing. Even at the max, I could not get it to be right on time, but it still was fairly close. But it had an adjustment that you could do up or down the mass to make it right. Never could get it exactly on, but it came pretty close. But all the period depended on was on the length of that thing. So if I screwed it up or screwed it down, I could have varied the length a little bit, but it never was enough. Okay, there is the period of the pendulum. Okay, and because it's very regular, it can keep time. Okay, and I think they said this Galileo is the one who discovered this characteristic. Okay, and that's all we got. Oh wait, there is an example, so let's go to the example. So let's get out of this and go to the example. If I can get the slide back up. Go from current slide. Okay. Find the length in centimeters. So we're looking for, ooh, I got to get my pen back. Keep forgetting that. We want the length in centimeters of a pendulum with a period of 1.5 seconds. What do we use to stand for period? What symbol? Capital T. Okay, it's 1.50 seconds. Okay? Now what's the formula that relates period to okay, T is equal to 2 pi, is that what you said? The square root of L over G. Where G we know to be, alright. Now we're looking for length in centimeters. So that's going to suggest to us that we use the SI unit for G. And what is that? 9.80 meters per second squared. Except we got a problem here, Houston. We want the length in centimeters. That's in meters. So we need to convert that to meters per second, centimeters per second squared. So we're going, second squares is fine. We're trying to convert our meters to centimeters. So what unit do we put where?
So we can't just move the decimal?
Yes, you can. Which way do you move it?
Which we move it to the left.
Okay. Okay, 2 places. So that would give you 980 centimeters per second squared, right? Absolutely correct. Okay? Because meters are much longer than centimeters, so you need a lot more centimeters to get the same thing, 980. So you don't need to do your conversion if you understand that. Good deal. Now we're ready to go. Except we're trying to get L, so let's solve for L first. That makes it, you can do it either way. You can plug or chug and plug. I don't care which way. Let's solve for L just to see what to do. First thing we're going to do is get rid of the 2 pi. So let's divide both sides by 2 pi. So T divided by 2 pi, there we have it. All right. Now we need to get rid of that square root. How do we undo a square root? Square. So we'll square this side, and that will make T squared over 4 pi squared. And here we just lose the square root symbol. So now we have L over G is equal to T over 2 pi squared. Okay, one more thing we got to do to get L by itself, a naked L, multiplied by G. Okay, done. Okay, so L is equal to T squared over 4 pi squared times G.
Well, it wouldn't still be 4 pi squared, would it? Oh, yes.
Square every bit of it. Right. Okay. So we're looking for L. So T is 1.50 seconds squared divided by 4 divided by pi squared multiplied by 980 centimeters per second. Okay? No, centimeters per second squared. I was going to say that doesn't work. Here the second squareds go out, and all the rest of them don't have any units, so it's going to be in centimeters. So if you'll do 1.5 squared, which is 2.25, I think, divided by 4, and then divide that by pi squared. Unusual thing to do on your calculator. And then multiply that by 980. What will be the length of your pendulum? Say again? 55.85. 55.85. It looks like we only have 3 significant digits, so we count off 3. 55.8. Look to the right. That's a 5. So round this up. Let's call it 55.9 centimeters. Okay? Yes, look at that. 55.9 centimeters. Now, they did it I don't know how they did. Yeah, they did it the other way. They left the meters per second squared in there and did all the calculations and then changed at the end to centimeters. So, same deal. They got 0.559 meters, which is 55.9 centimeters. We changed to begin with. Either way works as long as every step you take is correct. Okay. Then there's problem 16.6. The odd numbers of those have answers in the back. I would do as many of those as necessary to make sure that you understand what's going on there. There's a glossary there with a lot of words in it. There's 5 formulas on page 448 that you can draw on anytime you need them. There are a few review questions, multiple choice there, and then some that you just answer that help get you the concepts down, but the review problems are going to be closer to what you'll see on the test, and there are 17 of those, and I believe all those answers are in the back, aren't they? So you can do any of those 17 to help you when you're doing the test. Okay, now, we had several people come in that needed to get tests, so I don't have as many as I did before. So I'm making, this is the test for this chapter. Let me go make sure I can make copies. Do you need some of the other tests? Yeah, I don't know if I have any of them. Okay, I may have to run through some too, but let me get these. How many do we need? 1, 2, 3, 4. I'm going to make 5. I don't remember how many people were missing. Okay. Toby got one. Nicole and Caitlin. So I need at least 6. This is the first Wednesday I've been teaching here that they've locked both office doors. Okay, they usually leave it unlocked for the medical tech people who come in the evening. And she called today and said she wasn't going to be here, but she didn't say she was going to lock the office. I can't get in there to make copies. So, I'm trying to think what we could do. If some of you can follow me after class to the other campus, to West Campus, I can get to a copier there and make additional copies. Are any of you able to do that?
I can.
You can?
Yes, sir.
Okay, why don't you give yours to somebody who can't make it there? Does anyone can't make it to there? Okay? You can't make it. Then any of the others, we're not through. Oh yeah, you gotta leave. Okay.
We're not through.
Huh?
We're not through.
No. We go till 6:30. Yeah. Okay. All right. You got your test though. Can anyone else go to the West Campus after class? You can't. Can you? You what? Okay. All right. Can the rest of you go? You can't either.
I can go make.
Oh.
Oh, you know what? You remember Kobe took two, maybe
What's that?
he took two, or whoever that was, he took two with him,
Yeah.
maybe he set them down and forgot them.
Really?
I mean, I'm just guessing.
They were okay. These aren't yours.
Oh, I got mine. I was gonna take it.
Okay. Who else can't stay or doesn't want to stay? Okay. You can't stay or this would rather not. That's all I got now. Sorry. Can you run over? I'll make copies when we get there. As soon as we get out of class. Okay. Sorry about that. Like I said, first time it's been locked up since I've been teaching here. And I don't know why, because unless you found out the EMTs weren't going to come in tonight and locked it up. I'm sorry. Okay. We're through with chapter 16. That's the test. And by the way, I'm sorry, one person's already left. Number 8 and 9, you can see I wrote something on the side because they gave you the problems, but they did not give you the frequencies. So you couldn't figure out what frequency. So I had to do some back calculations. So number 8, a train traveling at a speed of 80 miles per hour approaches an observer at a station and sounds a whistle at 585 hertz. That's the whistle. What frequency will be heard by the observer? Okay? Assume the sound velocity in air is 1,090 feet per second. Same thing they did on number 9. A car is traveling away from you at 70 miles per hour. The car horn produces sound at a frequency of nothing. They left off the frequency there too. That one's 5,000 hertz. I've written it in, but that's what that reads. I wanted to make sure you understood that. 5,000 hertz. What frequency do you hear? Does that make sense for everybody? I've made the corrections on here, but I wanted you to make sure you understood what those things were. The whistle's frequency in number 8 is 585 hertz, and the car horn frequency in number 9 is 5,000 hertz. And you should be able to do the problem from there. All right, and we'll go make copies next time. All right, we move to chapter 17. So let me end this, and we'll keep that. We'll end this one, because that was the last slide, wasn't it? Yeah. So we'll end this one and go to this and chapter 17. And the next 4 chapters are in order. The first ones we were skipping around, but now we just finished 16, we'll do 17, we'll do 18, we'll do a little bit of 19. I think we'll have time to finish these. Chapter 17, basic electricity. All right. And let's see, I guess I'll show the first slide here. Okay, chapter 17, basic electricity. Yeah, this is probably as good a place to start as any. Okay? Now, Electricity as we know it, understand it, and use it is a fairly new phenomenon. People knew about electricity as far back as 2,500 years ago, okay? But all they knew about it then was what we call static electricity, which means, and here's what they did. They had, does anyone know what amber is? I know it's sort of a color, but the color comes from what it came from, amber. It's basically petrified or fossilized tree sap, okay, and that makes a yellowish solid, okay, and that's where the color amber comes from. When an amber rod made out of fossilized or petrified tree sap was rubbed with a wool cloth or fur, either anything such as that. Okay, a wool cloth, fur, something like that. When you did that, then you could pick up little objects with that amber object. You could make your hair stand up if your hair was dry, not too oily and stuff like that. It would follow the amber. Little pieces of paper would be picked up, that type of stuff. Or if you wanted to, you could sneak up behind a friend and get it close to their neck and shock them. Oh, and what joy that was, okay? Actually, that's what it was used for, parlor games, as people shocked people, you know. Didn't understand beans of what they were doing, and it wasn't hurting anybody, but it just came as a little shock. Now, when I was working at radon research at Southern Research Institute, we were doing a lot of our efforts down in Polk County, Florida, which is where Lakeland, Bartow, those kind of places are. And we usually stayed at one of the cheapest motels we could find, you know, because we had only so much research money to spend. We didn't want to waste it on luxurious hotels. And those typically had, you know, polyester carpet or something like that, rugs or whatever. And when you walked along, especially if you had, say, rubberized shoes, which is a fairly safe thing, walked on that synthetic carpeting, sort of dragging your feet a little bit, and reach for a doorknob, you would sometimes get a shock. Static electricity. Same principle of rubbing wool on amber. You would be transferring charges. Well, no one knew what you were doing. That's what you were doing. Some of the old vinyl car seats, scoot across them in certain cotton clothing or something, reach for the door handle, zip, you know, you feel a little charge. At one time, it was a little, you know, people worried about being charged and reaching for the gas thing and maybe the charge igniting. I don't think there was ever a recorded thing of that happening, but people were worried about it. What is happening there is that you are moving charges, okay? Well, what do we mean by that? And that gets down to an atom. That's what we have here. Atoms are made up of a certain structure. Now, these are not drawn to scale, okay? But your structure is, you have a nucleus. And the nucleus contains basically almost all the mass of the atom. I mean, all the mass, just about. Just a little bit's not in there. And it is incredibly tiny, okay? Incredibly tiny nucleus. And then there's a cloud of electrons around that nucleus, which have almost no mass at all, but take up a lot of volume. Which means, in between here is outer space. I mean, it's just as empty as outer space. I mean, there's nothing there, but that's most of the volume. And my older brother came home from college his sophomore year, before I went to school, and he came home saying, most of everything is nothing, you know, and that's what he meant. He had learned that in physics class, that most of the mass is concentrated in an incredibly tiny little nucleus and surrounded by electrons which have almost no mass, and yet they take up a huge amount of volume. So most of everything was empty space, okay? all the mass was located in that tiny little nucleus. Okay, now in the nucleus, there are two things. Well, there's more than two, but two major things. Protons, which are positively charged, and they're big, massive comparatively. And then neutrons, which have no charge, neutral charge. Okay? And usually, in most materials, there's more neutrons than protons. Not all materials, but most of them. And they're not showing the neutrons here. They're only showing the charged particles. Now, flying around that nucleus are these electrons, which have your negative charge. And even though they're incredibly tiny, no one can actually isolate an electron, so to speak, and know what you got, because it's so incredibly tiny, almost no mass, just a small fraction of a mass. It has as much charge as those great big old protons do. They have a +1 charge, the electrons have a -1 charge. Now, where did the plus and minus come from? You may find it interesting, Benjamin Franklin referred to electric charges as being positive and negative, and ever since then that's stuck. So here, our great American statesman, publisher, he published Poor Richard's Almanac, postmaster, our first postmaster general, I believe he was, ambassador. He was also quite a good scientist, okay? Remember, he's the one that flew the kite in a thunderstorm, but had a key on it, and he showed that lightning was indeed electricity. That's about all he understood about it, but quite a good scientist. He named the charges as positive and negative. And unfortunately, for us, he kind of named them backwards. He didn't know, and there's nothing wrong with it, but we'll talk about that later. Okay, so what happens when you rub amber? Now, this is a representative atom. It's not precise by any means. It shows 3 protons, no electrons, or you would have at least 3, neutrons. You'd have at least 3 neutrons in there, but it's not showing those, and 3 electrons. Now, that happens to be a lithium atom. Not that you really need a lithium atom for anything. You most of the time don't have lithium atoms for anything. It's a fairly rare element, but it does exist. And this is what we call a normal or balanced or neutral atom. As many positive charges, 3, as you have negative charges, 3. So it's neutral. Normal atom. Now, they're not showing this precisely, okay? If they were, 2 of these would be closer in, and one of them out here on the outer part. They just showed them all 3 about equal. They're not. 2 of them are usually closer, one of them flying around. That one that flies around on the outside, real easy for lithium to lose it, okay? But when it loses it, it no longer is a neutral atom, because now it has 3 positives and only 2 negatives, so it has a net positive charge. We call that a lithium ion, I-O-N, meaning charge. Atom, neutral, no charge. Ion has a charge, and that would have a +1 charge because it lost an electron, which had a negative charge. You never see this, ever see this. Lithium picking up an extra electron and becoming a net negative charge. If you went on across the periodic table to chlorine, say, chlorine has 2 in the inner shell, 5 in the outer shell. It wants to have 6. It wants desperately to have 6, and it'll pick up 1, like maybe stealing 1 from lithium. And now it'll be a net negative charge. But they're showing this as if it's lithium. If it ever did occur, this would be a negative lithium ion with a -1 charge. Okay? It's just that you don't usually see that in lithium. Okay? But they're just being representative here. Okay? So that's what they're calling them, atoms with positive charge and atom with negative charge. They're really ions with positive charge, ions with negative charge. If it's an uncharged atom, that's what you call an atom. Neutral atom. Okay. Now, there's two things that we do with electricity. One is just charge things, okay? And the other thing is to move the charges, okay? Now, most of what we do with it is moving charges. We're not even doing that yet, okay? We will in a little bit, but not yet. Right now, we're just talking about static charges, okay? Now, I mentioned the amber and the wool. You can do this, and you probably have done it whether you realize it or not. If you have a rubberized comb and you comb your hair, now your hair needs to be fairly clean, you know, not too greasy, okay, so washed fairly recently, but completely dried, okay, and it needs to be a fairly dry day. Here in the southeast, we don't have that many dry days, but we do have some. And on a very dry day, you comb your hair, and then you notice you pull the comb away from the hair, and the hair follows it. It's not got a tangle in it, it's just following it. The reason is you brushed electrons off of the hair onto the comb, and now they're oppositely charged, and they attract each other. So there's a characteristic of charges. Unlike charges attract each other, like charges repel each other. Okay? Now, you can take that same comb after you've combed your hair, just like you did with amber, have little pieces of paper or something like that there, hold it near it, and paper will jump up to it. Because the paper is neutrally charged, no charge, and it's attracted by the negative charge on the comb because you brushed electrons off your hair onto the comb. So it has a net negative charge. Now actually what happens in the paper is neutral, but it has electrons in it, and the electrons are repelled by the extra electrons on the comb, which means the sites near the edge up here are deficit of electrons, and these are excess electrons down here, so this positive side of the paper gets attracted to the negatively charged comb because you've now distributed the charge on the paper because like poles repel, like charges repel. Okay. Now, that's static electricity. You all know about it from your clothes in the dryer, right? Synthetic materials in the dryer and cotton materials in the dryer stick together like crazy, okay, right? And you get sometimes they'll stick to your legs, you know, or something, and you have static cling, right? All those are examples of static electricity. When you have moving charges, that is called conduction. A moving charge is conduction. Well, let's see if they have a slide like this. Not quite yet, okay? We'll go into that in a minute. When you transfer a charge from one object to another. Yeah, I guess this next slide is this. So here what we have is, and this is called an electroscope, so you don't really have to know that name. Here we have a ball, and it's called wood pith. Now, I'm not absolutely certain what wood pith is. I think it's fibers from wood that they've shaped into a ball. You know, you maybe added acid to it and stuff like this and shaped it into a ball. I think of a pith helmet, you know, like they used to wear on safaris in Africa. You know, it was made out of a paper-type product. That's, I think, what they call wood pith. So here you just have a ball of that wood pith. And you're hanging the ball is free to hanging there. Okay? Now you take a rubber rod that you've, again, rubbed against something, maybe fur, possibly wool, something like that. It acts like the amber, and you've knocked electrons off of your hair, or off of the wool, or off of the fur, or whatever it's been doing, and you have excess electrons on the rubber rod. Well, that ball is neutral right now, but you put this rubber rod that has excess electrons, so it's negatively charged, touch it to the ball, and now and the ball becomes negative because those excess electrons move from the rubber to the ball. They're trying to get away from each other. There's too many electrons on that rubber rod, so they try to get over on the fifth ball. Well, if you do this to two electroscopes, that balls are hanging freely there, bring them close to each other, then the balls move away because they're both negatively charged. Negative or like charges repel each other. Okay? Now, rather than doing that, what if we had a glass rod and we rub it with silk? Silk happens to pull electrons off the glass rod, okay, making it deficit of electrons, which means you have extra positive charge. You touch it to the pith, neutral pith ball here, okay, and now any electrons that are on here try to go there and fill the places where there are missing electrons there. So both of these wind up being positively charged, okay? You bring that one near this one, and now you see the balls attracted to each other. Because unlike charges attract each other, like charges repel each other. But do this to a second one, bring those close together, and again, like charges repel each other. Unlike charges attract, like charges repel. When you touch these, this is called conduction. You conduct the charge from this to that. You have to touch them. Have to touch them to have conduction. You can induce a charge by not touching, but you can't move the charges without the touching. Okay. So I've just gone to 17.2, which is talking about induction. Okay? Now, here's another electroscope. This doesn't have a pith ball. What it has is a metal ball up here, a metal stem. Everything pretty much is metal, except in here, they use gold foil leaves. Okay? Now, it's a metal case. Everything's metal. Not down here. This is insulated down here, but that's beside the point. Okay, so let's go back to our rubber rod that we've rubbed with fur or wool or something like this that got excess electrons on the rubber rod. Okay, you take that and you bring it close to, don't touch it. If you touch this, that would become negative. You bring it close, and what happens? You're not touching it. Well, let me hit another important issue here. Electrons in some materials move very freely. Other materials, they don't. Metal, they move very freely. Okay? So everything here is metal, including the gold leaf. There's two little strips of gold leaf there. You know what I mean by gold leaf? It's like aluminum foil, but it's gold, and it's even thinner than aluminum foil. It's just what they do with it sometimes. You get, it's such a thin thing, and you can just rub it onto another metal, and it'll just go right onto the metal.
You can buy it in sheets.
Yes.
Like we actually have a piece of furniture that has gold leaf on it.
Right.
Has been repaired, part of it.
Exactly. That's exactly what it's used for. These gold picture frames you see, they're wood, but they've taken gold leaf and rubbed on it, and it looks just like gold. Except it's not. I hope it's not nearly expensive. Okay. Those gold leaf, I bet you, is pretty expensive too, isn't it? But not as expensive as pure gold would be. So it's also a metal. So what you're doing here, you're bringing this rubber rod with excess electrons here, close to here, and these electrons here flee because the electrons repel each other. The negative charge repel each other. And the electrons have to go somewhere where everything here is connected except those two gold leaves. The excess electrons go there, and as soon as they do, they split apart. They were hanging happily like this, and now they split. You didn't touch a thing, okay? You just brought it close. Now these electrons flee away from here, and then the gold leaves spread apart. because those excess electrons, that's as far as they could go. They can't go any further. That's all a circle, and they spread apart. That's induced negative charge creates the repelling situation there. Do the same thing with the glass rod. You rub the glass rod with silk. The silk has pulled the electrons off of the glass rod, leaving the glass rod slightly positive charge. Bring it close, but don't touch it. And because the electrons move really freely in the metal here, all the electrons go rushing up here because this is short of electrons, and they try to get as close as they can. They don't touch, get as close as they can, and when they do, they leave here, and you have two positive charges, and the gold leaf spreads again. Now, you can't tell what charge you have there, but you know that's negative, that's positive, produces the same result, that the gold leaves spread, because they now have like charges. Like negative, spread, they repel each other. Like positive, spread, they repel each other. This is induced. You're not touching. If you touch, that would be conduction. Okay? But bringing it close, that is induced charges. You have to have a conductor, and that's why I mentioned conductors. Metal is a good conductor. Electrons move very freely. Okay? The glass, the amber, the rubber, they just accumulate there, but they don't move all that freely. Okay. Now, let's see. Yeah. This is a picture of the next page. So you had your rubber rod that was excess electrons, got it close to the metal, chases those electrons away. They move away, get down here on the thing. Now, if at that moment, when they're spread like that, you're not touching there, but now you reach your finger over and touch this part here, you are a good conductor. What are you made of? Mostly water. And water dissolves things really nicely. And what method does it use to dissolve things? Water, remember, didn't we talk about this before? Two positive hydrogen, one negative oxygen. And they're at one end and the other. So water is what we call a polar molecule. So it separates things that are easily dissolved. Things like salts and things like that you can separate in positive ions and negative ions. Water does a great job of dissolving them. And guess what? Most of the water in your body, a lot of it is blood or other fluid, body fluid, okay? And that's all got dissolved materials in it, okay? So you're a great conductor because that water conducting those salts is a great conductor. So you touch this, and you probably don't feel anything because it's a very small amount of charge. And when you touch it, electrons from you, they did this backwards, didn't they? Okay? All right. This is positive, so you touch it, electrons leave you and go, they did this backwards, okay? Leave you and go over here to the thing to try to neutralize it. As soon as you neutralize it, then the gold foil goes back together because it's no longer neutral, okay? No, I'm sorry. The electrons, they did it right. Excess electrons are here because you got them there. And you conduct the electrons away, and you're grounded to the floor or somewhere like that. So you pull them off, okay? So now you get rid of those excess electrons that were on the charges here. But then, okay, pull your finger away, and everything's neutral. Things are fine here, okay? Because the electrons have left, and this went back to being neutral again. The excess electrons, okay? Now, as long as that pin's close, it's fine. I mean, the rubber. Pull the rubber away, though, and now you have a net positive charge there because the electrons left, and now the full split spreads again. Okay? You conducted away excess electrons here, allowing these to go back together, but when you pull this away, now you have net positive charge, and the full split spreads again. That's, again, this was induction, okay? This was pulling away electrons by touching it. Then you have electron shortage here then, but it doesn't realize it. It thinks it's neutral. When you pull this away, then they spread apart again. Okay.
So when you touch something and you actually feel a shock,
you may not. This was so little charge, you may not feel it.
Well,
But if you do feel it, yeah.
when that happens,
Yeah.
is that an example of you pulling it away?
You can't tell. You just know that there's charge being transferred. So when you, like your cheap hotel, scooting along that polyester floor, I don't know, I'm guessing the rubber shoes probably pick up electrons off the poly, so you probably are net negative, and then you reach and touch the doorknob. And actually, I mean, this is heavy. If it's night and it's dark, you see the spark.
Well, why do you so often, why is it that it seems like one is shocked more in the winter?
Because the air's drier. Okay? Because you're heating up and you're taking moisture out of the air. Relative humidity is less in the wintertime. In the summertime, it's hot and humid, so the charge gets leaked away. Huh?
The air's more dense.
Yeah, and the water leaks the charge off. Yeah, yeah, that's the, and that's why clothes coming out of the clothes dryer are more likely. The wet clothes, they don't stick together, but when you dry them and you remove all that moisture, you don't have it. So now they have all those excess charges in there, and that's what the dryer sheets do. They kind of collect those charges, so your stuff comes out and doesn't stick together as badly. Okay.
And it does it more in the winter.
What's that?
I said, and the static is more in the wintertime.
In the wintertime too. Yeah. Okay. Yeah. And so those things do stick, but you're absolutely right. They do it more. Now what you can't tell is whether the charge is negative or positive, because the attraction is between unlike charges. So you don't know which has the excess of what and which has the deficit. You just have the sets of charge.
But is it an example of induction, or you're saying you don't know that? Like, I'm just asking.
Oh, I see what you mean.
Is it, like, when that occurs,
Yeah.
is that
Okay.
an example of induction?
Okay, I see what you're saying. Walk across the cheap carpet, the polyester carpet, and reach for the doorknob. Now, as long as you don't get too close, then, and you'll sometimes feel this, you'll sometimes feel a little bit of a tingle there if you get really close. What's going on here? Because now you're inducing the charge. Say you have excess electrons, they're getting ready to escape. You get a little closer and they jump, and that's when you feel the charge. That's the shock. Now what you do, this wouldn't work. If you held the key like this it wouldn't work. If you held the key like this, or if it's an all metal key, you come up and you close to the door. Now the charge goes from you into the key, and it jumps across, you don't feel a thing. Because you're just a pathway then. You're not a potential difference. We'll get to that later. The potential difference is between the key and the door. And that's what I used to do all the time. When I got close to the room door, held my key to it, and again, at night, you could see, and you could hear it sometimes, that little spark go across there. I think a lot of the nicer places, they probably have carpets that don't do it as badly, because I've never felt the shock recently. But then, too, there's not as much metal. This is back when everything was metal. Now they have key cards, so, the doors are probably not. Okay? That's the very thing that's happening with lightning. Clouds moving, rubbing electrons off of one onto the other. They build up a big potential difference, and then they discharge. And that's what lightning is. Same thing as that key or your finger going toward the door. That's static electricity. Now, induction up to the point before the discharge, conduction when it does discharge. Yeah. To answer your question. Okay. The big key here is like charges repel each other, unlike charges attract each other. Okay.
So would we be both?
What's that?
Would we be both? Because
Yeah, you're doing conduction of electrons away, and you've still got the thing close to it, so that's inducting, and your finger's doing conduction. Yeah, exactly. And you pull your finger away, you've already bled off the electrons, and now the thing over here doesn't know it. It feels like it's neutral again because you still got that negative near it. Pull the negative away, and whoops, I'm positive now. So the Gulf oil splits again.
We used to see a chiropractor in Nashville that basically said your body was, full of electrical impulses.
Right.
And so he actually did things to desensitize my son to his allergies. And I'm just thinking about it. I guess it really has to do with those
Yeah.
impulses, the way
Yeah, exactly.
and he could truly basically rewire him.
Right, right.
What he did.
And that's for allergies, you said?
And it worked.
Interesting. Wow.
It worked. It was crazy. I mean,
Yeah.
but
Did he feel much when it was happening to
I
him?
didn't feel anything when it happened, but we actually had to bring in this thing that he was allergic to,
Yeah.
grass.
Uh-huh.
So we actually brought in grass from our yard because he was
Right.
allergic to grass. And he rewired, he did this series of stuff to him.
Right.
And then after that, he was totally desensitized. He could mow the yard, he wouldn't have an attack.
Wow.
He could wear like a bandana.
Nice.
But it's just odd to think it truly is the fact that it's these charges, right?
Yeah, yeah. I didn't know allergies were that sensitive to charges, but wow, that's interesting. Now, I have heard about allergies that has nothing to do with static electricity. Another thing that sometimes, if your pollens are what you're reacting to, your allergy, people, eat local honey because the honey bees, they do all that stuff, and you get your body pumped up with the things, and now you don't. I've heard that really improves.
I heard also letting your child play in dirt,
Yeah,
local dirt.
Yeah.
That's really good with germs.
yeah, right. And there's, yeah. I've also, now this has nothing to do with this, but I just heard recently a lot of reports about this of mothers giving natural birth as opposed to cesareans. And they really feel like a lot, or at least it's a theory now, that a lot of the initial exposure to a normal biome comes through the birth canal, and that they are now testing to see if babies that are delivered by a cesarean, if they swab them down with material from the birth canal, if that won't help their later allergy type situations or other immune.
Because my first child, I did have a cesarean section,
Uh-huh.
and she really,
Right.
her allergies were really bad. But my son,
Yeah.
basically doesn't have any. It says
Right.
he doesn't
Yeah.
have any problem.
Now that could be genetic. We don't know for sure, but there's a lot of evidence suggesting that maybe they pick up natural biomes through the birth canal, which is so, and there's good bacteria, bacteria are not all bad. Your gut is full of good bacteria. Your saliva is full of good bacteria. That's how you digest food and stuff like this. So you're full of good, of good bacteria, and there is another place where it is. But if you're minus that, then you may come out imbalanced. Now, not guaranteed that's why, but it could be. Okay. Now, back to this. Here's a couple of examples. Now, let's see. They don't show the lightning here, I don't think. No. Okay. The picture of lightning, and that's the same type thing as before. It's like scrubbing your feet across the cheap carpet, reaching for the doorknob, the little spark comes. Same thing, lightning. Clouds moving across each other. One takes off electrons, one loses, gains, one loses. They build up what they call a potential difference between the two, and then lightning is when it builds up so great it discharges. Now, there's actually three types of lightning. I don't know if you've ever realized this. There's cloud-to-cloud lightning that you see spider web across the sky sometime. But there's also cloud-to-ground lightning, which you usually see and you anticipate that. But then, believe it or not, there's ground-to-cloud lightning. Okay? And I've seen a couple of pictures of someone happened to be snapping a picture right when a thunderstorm was in the area, and you got a picture of that lightning strike. It's coming from the ground going to the cloud. You see it heading that way. It's amazing because the excess electrons are in the ground, the deficit's there, and they're moving that way. Now, if you're in that spot, it'll kill you either place, whether it's coming or going, but it's really phenomenal. That is one major lightning strike that you see in your book there. That's amazing. There's a lot of voltage in that. But we'll get to that later. This is a device they call a Van de Graaff generator. And it was named after a guy named Van de Graaff. I think it was Dutch or something like that. What it is, you have a rapidly moving belt here, and there's brushes at the bottom, maybe at the top too, I don't know. And that belt moving is a lot like the rubber comb or something like that and it's building up negative charge, okay? And yeah, the comb is up here. The collector comb is up here. It's building up negative charge there. Now, these kids are standing on something that is not grounded, okay? It's insulated, okay? And they're perfectly happy to be building up extra negative charge. What they don't want to do is take their hands off. Then they're going to get shocked like crazy. Not harmfully, but you see their hair is standing up because those extra negative charges are going as far as away from each other as they can. That goes to their hair, and their hair are all negative charges, so they get away. You'll sometimes see just a whole halo of hair around them. These aren't, the guy seems to have a little bit more, maybe his hair is shorter, but you see all of that is happening there, okay? And that's what's happening with a Van de Graaff generator. Same type principle.
But what's the point of it?
It's just to show static charge,
Okay.
build up that's all it's doing. And kids love it, okay? To see their hair stand up like that. All right. Now, this phenomenon is described by a French physicist named Charles Coulomb, okay? Oh, wait. I had never noticed this. Robert Van de Graaff, I said he was probably Dutch. His family was Dutch. Read that little blurb there. Physicist, born in Tuscaloosa, Alabama. Amazing. He invented that constant potential electrostatic generator, later known as the Van de Graaff generator. Later developed this generator for use as a particle accelerator. Those are really high voltages there. He invented the insulating core transformer in the late 1950s. I never knew he was an Alabamian. Wow. Amazing. But Charles Coulomb, born in France, I got that one right anyway, and he studied and hypothesized some about these charges, okay? Now let's go back mentally anyway, I won't go back on the slides, to those charges. Now I was almost expecting someone to say, well, is it always electrons that are moving, or do you sometimes gain or lose protons? What do you think? Only the electrons. Why? They're out there in that cloud, remember? If you gain or loss a proton, that comes from a nuclear reaction. Let's not have any of those, okay? That would be major blow up, okay? So it's always the gain or loss of electrons, never the transfer of protons. Ever the transfer of protons. Always the changing of electrons. So there's charge on the proton, and let me get a little bit of this in here. Let's see, yep. Let me get this back to black here. The charge on a proton is, I usually write it like this, but the book says it's E plus. Now, what E stands for in this case is not your exponential function or something you might have done in math. This is a single basic unit of charge, 1 electron charge. Now, if it's a proton, it's a plus. If it's an electron, it's a minus. So I usually reserve that to represent an electron, that to represent a proton. The book does E plus or E minus. This would be the charge on a proton. Okay. Now, that is the smallest unit of charge you can have and be a charge. Okay? That is a single electron charge. That is so incredibly tiny, no one can actually measure that. It's too little to even measure. Okay? But the larger unit, that's something we could measure, that's named the Coulomb, named after Charles Coulomb. So it's a capital C. Now, I think I may have mentioned before, capital C, if you have a degree symbol by it, that's named after Anders Celsius. That's a measure of temperature. Without a degree sign, a capital C is a Coulomb, and that's a unit of charge. Much, 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 much bigger than electron charge. In fact, one proton charge is plus 1.60 times 10 to the, now catch this exponential, negative 19 coulombs. So a coulomb, it takes something on the order of 10 to the 19 or so. That would be 1, 0, comma, 0, 0, 0, comma, 0, 0, comma, comma, yeah. 6 groups of 3 zeros and a 10 in front of it. So that would be, I don't know, 3 would be 1,000, 6 zeros would be 1,000,000, 9 zeros would be 1,000,000,000, 12 zeros would be 1,000,000,000,000. You got 18 zeros there. Something, 1,000 trillion with another 10. So 10,000 trillion electrons to make 1 coulomb. Okay, something on that order. I mean, an electron charge is incredibly small. A coulomb we can measure with our devices. Okay. On the other end, the electron charge is minus 1.60 times 10 to the minus 19 coulombs. Incredibly small charge. So, I'm sorry, I said 10 to the 19, it's 10 to the 18. So 6.25 times 10 to the 18 electrons make 1 coulomb of charge. Okay? And that is exactly the reciprocal of this. 1 over 1.60 times 10 to the 19 gives you 6.25. So 6,000 trillion electrons. 625, no, 6,250, no, yeah, 250 trillion electrons makes 1 coulomb of charge. It's an incredibly large number. Okay. That is a charge of 1.00 coulombs. And that's what we usually measure is coulombs, not electrons. Now, just to get it in perspective, anyone remember what we mean by a 100-watt bulb? I mean, when it was an incandescent bulb, most bulbs now are either compact fluorescents or LEDs, but the good old light bulbs that we used to have that had a filament in them, a 100-watt bulb, that would be the amount of charge that passes through a 100-watt bulb in about 1 second. So it's a lot of electrons, but electrons are incredibly small and they move very fast. Okay. Now the symbol for charge is Q. When you see a little q, that means charge. it would be so many blah, blah, blah coulombs of charge. You could have it as electrons of charge, but usually it's coulombs of charge. All right. Now, I think I've mentioned to you before the inverse square law. Does that ring a bell? No. Okay. If I had said it, I probably gave the illustration of my wife likes to hook a little reading lamp on her Kindle or on her book and read when she's supposed to be sleeping. When she's in bed. She wakes up in the middle of the night, clips that on and reads. And that lights the book or the page or the Kindle well enough for her to read, right? Well, could she hang it from the ceiling and read it from there? No. Because the light dissipates at 1 over the distance squared. That's called the inverse square law. Well, Coulomb determined that the force due to the electron charges and things like this falls off as 1 over r squared. Okay? Inverse square law. And I guess that may have been the first time this was discovered, and then later we found out everything followed that too. Sound, gravity, everything follows an inverse square law. Okay. But he determined it, and this is called Coulomb's law of electrostatics. Okay? And it's dealing with forces. And I think what I'll do is get off of this page. We never did actually get to this page, but get off of this page. That's not what I want to do. This is what I want to do. Okay, not that either. Okay, that. Okay. Keep getting my buttons crossed up. Whoa! We have 1 minute left. Let me just give you Coulomb's law, and it shows the inverse square. Okay. No, we were that short of time. Here's Coulomb's. It's called Coulomb's law of electrostatics. It's what governs all that static electricity and lots else. F, that's force of electrical attraction or repulsion, is equal to K, that's one of those proportionality constants. And this one happens to be called Coulomb's constant. And it would be Q1 times Q2 divided by R squared, where R is the distance between the charges. So F is the force of attraction or repulsion, either one. Okay? K is Coulomb's constant, and Coulomb's constant is 9.00 times 10 to the positive 9 Newton meter squared per Coulomb squared. I can't write. Okay? That is what the constant is. Now, I don't know if you remember a similar constant for gravitational. When we talked about, did we talk about gravitational attraction? It was incredibly tiny number here, whereas this is a pretty large number, meaning that electrostatic force is quite large for the, comparatively anyway. And what we'll do then is the Q1 and Q2 are the two charges that are being attracted or repelled. So we'll begin next time with that first example, example 1, bottom of the page. There's a little activity here. You can try that at home if you like. It's not really all that crucial. Okay. Any questions? All right. Now, remind me, yeah, good deal, thank you. Oh, and some of you want to follow me over and get copies, right? Thank you. So let me hurry this along. Let me turn this off.